always enjoyable to come to Lake and also invited by Nicolas, other organizers, but Nicolas was my first student. All this topological recursion formalism. So it's a great pleasure to be here. Well, I'm just invited to talk about quantum curves because this conference is about quantization. And there is, of course, a very deep link between topological recursion and quantum curves. However, I must tell you that doing it in less than 2 hours is a very big challenge. And so I will probably not right to the end, and I will not be able to give a proof of quantum curve because there is just not enough time, and we have many things to introduce. Well, I know that many people in this room are real experts in topological recursion, but probably some of you hardly know what it is about, so I will start by doing an introduction. On the two boards at the top, I will write examples, and I will always come back.
Recording in progress.
Okay, I will always often come back to these examples, and typically, what is topological recursion about? So let me start by an introduction. What is topological recursion? Topological recursion is a procedure, as the name says, it's a recursive procedure that assigns, that starts from initial data and creates a sequence. The initial data is the spectral curve. So, spectral curve. And topological recursion will be something that to a spectral curve gives a sequence. So let's call a spectral curve S, and you will get some a sequence. In fact, it's a double sequence, omega gn of x, with g from 0 to infinity and n from 0 to infinity. And it will be a recursion on, in fact, 2g minus 2 plus n. Once the name topological. However, so what is a spectral curve? So here you have just two examples. A spectral curve, in the first way, just let's think of it as a plane curve, an algebraic plane curve. So example of spectral curve, just think of an algebraic plane curve given by an equation p of xy equals 0. So just this example is the curve y squared minus x equals 0, and you see that it admits the parameterization with x of z equals z squared, y of z equals z. It's a way just to write this equation in a parametric way. In this one, the equation is at the top, y squared equals x cubed minus tx minus v, it's the Weierstrass curve, and you can parameterize it with the Weierstrass function p. I will come back to that later, and it's a torus. Topologically, it's a torus. So start from an algebraic curve, and compared to what Jörg Teschner was saying yesterday, this algebraic curve can be thought of as the characteristic polynomial of a Higgs field. So let me just take your favorite spectral curve at the moment. And to it, you will assign a sequence of differential forms. So in fact, omega gn, each omega gn is a one tensor one form. Okay, so it's a one form it's an n tensor form, and yes. And what is the relationship to quantization? So imagine you have defined such forms. So for the moment, it's a very informal introduction. Now let me define the wave function. Imagine that you have already computed that, and let me define a wave function. So it will depend on my spectral curve. It will depend on a variable that let me call it z, or x. Let me call it x, and it will depend on it will depend on a parameter which let me call it h bar. While its only role is to be a small parameter in which we shall write expansions or formal series. And let me write it this way: it's exponential sum over all g and n, h bar to the 2g minus 2 plus n over n factorial. That's in the exponential. And omega gn sits in a n form. It's a one form in each variable. You can integrate it n times. And integrate it from infinity to x. So in each variable, integrate it from infinity to x. So that makes a function of x. In fact, it's not truly a function. While the log of psi is a formal series. In fact, these formal series are typically divergent. Typically, the general term grows like 2g factorial. So in fact, it has Saclay index 1 in the sense of what Ricardo was saying yesterday, and it's a divergent series. To really make sense of it, you should use resurgence. But as a formal series, it is well defined. So in fact, log psi is, well, in fact, h bar log psi is a formal series. Well, let me write it, belongs to C of h bar.
What about the path of integration?
Sorry?
What about the path of integration?
Well, let me be very sketchy at this level. We'll talk about that later. Indeed, that's relevant.
The notation, so zeta in the dependence, that's the curve, or what?
Sorry, S is the spectral curve. So think of an.
So you're writing this as an argument of psi?
Well, I mean, psi depends on the choice of your spectral curve, since the omega gns depend on the choice of your spectral curve. So everything depends on the choice of spectral curve. Okay. So now, what is the relationship to quantization? The idea is that is to show. So, what is the purpose of the quantum curve question? Is to show that there is an operator that annihilates that psi. And the operator that annihilates that psi can be written. So, the question is there an operator, let me call it p hat of, well, it will depend, of course, on h bar and on the spectral curve, but it will be a function of x on h bar d over dx that annihilates psi. And you want a little bit more because, of course, there always exists such an operator. It would be sufficient, for example, to take psi, d psi over dx divided by psi. That would immediately make an operator that annihilates psi. But if you do that, it will be a full h bar series with singularities that could grow with the order of h bar. And so it's not manageable. I mean, what a good operator is that you really want it to be algebraic, to be polynomial-init, let's say. You want it to be polynomial-init. And in fact, you would like that the symbol of p hat would be p, well, plus O of h bar. So if you formally replace h bar d over dx by y, you would like to recover the same p you started with. Take h bar, so if you replace h bar d over dx by y and take the limit h bar goes to 0, you would like to recover the initial curve you started with. And the other requirement you ask is that p hat has has a good behavior. So basically it's polynomial in x to each order in h bar. So p hat is itself a series in h bar, and it should be a polynomial whose coefficients are series of h bar. So the answer is yes. So let me show you the example that I have here. In this example, when you compute psi, you can indeed find that p hat, so in this example, p hat of x and h bar dx is h bar dx to the square minus x. And that annihilates on basically you find that h bar d2 over d square psi equals h psi. So if you run all this program, so if you compute for this curve, if you compute the reagents, compute this psi, and compute h bar d over dx square minus x applied to psi, you will find that to each order in h bar, you find 0. So this operator annihilates psi as a series in h bar. Question, can you do the same for other cases? For example, for the parameter that I wrote up there, can you find it? And in fact, very often what you find is, in fact, what people are interested in is slightly more general, because having an operator that annihilates psi is nice. That's called the quantum curve. So you see why it's called quantization of the curve, P of xy, because basically, formally you replace y by h bar d dx, and that's more or less why it's called the quantization of the curve. However, in fact, we need a little bit more, and we need really an integrable system. And there is a very deep relationship between quantum curves and integrable systems. And in fact, let me define a slightly more general object. Let me define a matrix psi of, so it depends on h bar, it depends on the spectral curve, and it depends on x. Okay? And for that, let me, again, I'm very sketchy at this moment. This is just the introductory part. So it's a matrix. And it has questions ij. And before, so P of xy equals 0. If you look in the xy plane, it's a plane curve. If you draw the locus of solutions of the zeros of this polynomial, so this curve is the locus of zeros. It's a one-dimensional complex curve. In fact, it's a surface. Because x and y are in it's C cross C, it's not R cross R. But the thing is that for a given x, there exist several images. Let me call them Z1 of x, Z2 of x, Z3 of x, and so on, up to the degree of the curve. Okay, and so the indices I and j will run through the number of sheets. And so the matrix that I have here is so exponential sum over gn, h bar to 2g minus 2 plus n over n factorial, integral omega gn. And here I will integrate, the endpoint of integration will be the jth free image of x, so zj of x, zj of x. And the starting point of the integration will be the point at infinity. But again, the point at infinity may have several preimages, and let me call them infinity I. And that makes a matrix. Well, it may happen that these points at infinity may be degenerate, and you have to regularize a little bit, but let me be sketchy at this moment. That makes a matrix of formal series of h bar. And now the question is there so the question now is there a matrix, let me call it D of, so it depends on h bar and s, but it's really a function of this x, such that h bar d over dx of psi equals d psi. Or another way to write that is divide by h bar multiplied by dx. It would be by d minus 1 over h bar d of x dx psi equals 0. And so this is a connection. Blah, blah. So is there a connection which is polynomial in X or rational in X that annihilates this psi? So in other words, is psi a flat section of some group bundle, some principal group bundle?
Well, I think you mentioned that, but how do you define this when infinity is a ramification point, like the Airy curve?
Okay, in the Airy curve, precisely, the infinity is ramified, so in fact, you have to make a regularization. Let me avoid that. In Palvel, it's also ramified, so let me skip that for the moment, but there is a way to make it well. If you want, just replace infinity I by a point, let's say z prime I very close to infinity, and then you will take the limit where this point goes to infinity, but then the two lines will go to the same place. So for the second line, somehow subtract the first line, and so it's like taking the derivative with respect to that point. Okay. There is a well-defined procedure. In fact, all this was written in our article of 2007. So, and in the case of Airy, of course, this matrix, you can find it. This matrix is the matrix. So D is just the matrix 0, 1, x 0. And indeed, if you compute, it's very easy, and it's related to the Airy function. So in fact, in this case, S0 is called the Airy curve. Very often we call it the Airy curve. And just because psi, in that case, psi is just the Airy function of h bar to the 2/3 x minus 2/3 x. If you do a formal h bar expansion of Airy function, you recover exactly that.
So starting from the second order differential equation there, we can take two solutions, and then by the solutions and the derivatives, we can form this two-by-two matrix.
Yeah.
Is it exactly one?
Yeah, exactly. Well, the different solutions correspond to choosing the different preimages of X.
And different infinity somehow amounts to take derivatives?
Sorry, different?
Yeah. Well, if I change this second order differential equation into a matrix first order differential equation, I have to make a column psi and the derivative of this.
Yes. So somehow here you can do elimination to recover the quantum curve. So if you see what this, so if you want to see what happens, what this d over dx does on the, let's say, first entry of that matrix, you will recover the differential equation. I will answer, but just let me make a comment. Vice versa, if you start from the quantum curve, you don't have a unique system that corresponds to that quantum curve, indeed, because in the second line you could put almost whatever you want. So which means you have an indetermination of what gauge you take, but only some nice, but there are some nice gauges for which you get d to be a rational function of x. It's not every gauge that's nice. So you have to choose the good gauge. However, so I will answer your question, Anton, but just let me say that, so there is a good choice of it. But let me just mention that in all the cases where it could be proved that topological recursion leads to a quantum curve, in all cases where this was done, in fact, we went through this, the proof went through this part, which is to find a system, not only a curve. So in fact, the quantum curve was always a byproduct of finding a system. In fact, finding a system to me seems much more fundamental. So finding this connection is much more fundamental than finding the quantum curve. In fact, all proofs, as far as I know, all proofs which led to quantum curve, in fact, first found a system or a connection.
Yeah, my question is very technical. When you show something at the bottom of a lower board, you don't see anything.
Oh, okay.
So Yeah, that's much better.
Okay, sorry. Then I should have answered in English.
So, ask about this relation between equation and between matrix equation and quantum curve. So usually, if we try to pass from one to another, we can get some apparent singularities.
Yes,
so,
indeed.
Does it happen in this topological
You can
equation?
have apparent singularities, and again, there are some better choices of gauge where you can kill some apparent singularities. And indeed, this is really part of the question. So, I mean, a polynomial system can be, indeed, if you do elimination and want to get an equation for, let's say, the first entry of psi, very often you will get an apparent singularity in the p hat.
Typically,
Although p was polynomial.
typically, the number of apparent singularities is the genus of the spectral curve.
Yes.
So here it's genus 0, you don't have any apparent singularity.
No, you have apparent singularities if you choose. Well, but very good choices of gauge. Okay, let me, so now I cheated you a little bit. What? So I was very introductory, and when I say you want to satisfy a quantum curve equation or system, I mean order by order in H bar. We are in the world of formal series. So what I mean is that this should eliminate psi order by order in H bar. In fact, that doesn't work like that. This is in fact wrong. So in fact, for most cases, this conjecture is wrong. It doesn't. So if you define psi this way, you cannot find an operator that eliminates psi because you stay with formal series. In fact, you should go to trans series to satisfy the conjecture. You need to introduce non-perturbative terms, but we will discuss that at the end. So in fact, here, you see that psi. And that's why I multiply by h bar. Because psi, the first term in psi contains an h bar to the power of -1. So you have an exponential of a negative power of h bar. This is typically what you have in trans series, not in series. This is not a series, this is a trans series. So in fact, now you should ask the same question, not with series, but with trans series. So is there a way to define from topological recursion a trans series such that there is a quantization of P, or such that there is a differential system that annihilates psi as a trans series, and also, in fact, this system is very closely related to integrability, to integrable system. And it's very closely related to Hirota equations. Okay. I will not enter the details, but or to Riemann-Hilbert or to many other things like that. So now let me be more precise. Let's give the introduction and let me be more precise about what we mean. So 1.1 is, 1.2 is spectral curve. So I will really now give a definition of what I call a spectral curve. A spectral curve for me will be, so a spectral curve S, so definition, a spectral curve S is the data of several things. It's the data of a Riemann surface, let me call it sigma. It's the data of the function. Well, in fact, I'm sorry, I very often confuse the function x of z with the variable x which is in the plane. Normally I take two different notations and I should. So let me put straight x here and the straight y there. So it's a function x, a function y, or writing leave some space, and a function on something called v, where sigma is a Riemann surface. In fact, in the full general case, it needs not be compact, it needs not be connected, it needs not be, it can be almost anything. But here I will stick to compact in this lecture. X is a ramified cover, is a map that goes to a base curve, sigma 0, but in all my examples here, sigma 0 will be CP1. And it's a ramified cover, which corresponds to that picture. So sigma is the curve up there, sigma 0 is the base, and x is a projection from the curve to the base. And this is a ramified cover. In particular, it may have ramification points, like there. Okay. And it's a holomorphic. Okay. In fact, y. In fact, y could be a function. So here, y will be the projection to the in the other direction. But in fact, let me multiply y by dx and make it a one form. And then it will be a projection not to c, but to c times dx, which is the cotangent plane of sigma 0. So in fact, y, and so now let me write it y dx. So it's a one form. It's a meromorphic one form. On sigma. And if the curve is compact, there is an algebraic relationship between y and x. There must be an algebraic relationship between y and x. Okay. On B is something that, well, you see in all my examples, it depends on it is a function of two variables. It is a one-form tensor, one form. It is symmetric, and it has a double pole when z1 equals z2, so on the diagonal. Here as well, in this other example as well. Because the Weierstrass function P has a double pole at 0. So B, well, let me write it as it belongs to. So it's a function of two points on the curve, so it's the curve tensor times itself, and to k sigma tensor k sigma, and it must be symmetric. It must have a double pole on the diagonal. And let me make it so this 1 means that the residue of a double pole must be 1. So the coefficient of 1 over z1 minus z2 to the square. So 1 is this 1, if you want. Yes. So also, very often people write it this way. So you have sigma, you have a projection to sigma 0, which is by the function x. Okay? And in fact, in each point of sigma, you can associate not only its value of x, but also y dx. And y dx is the cotangent vector. It sits in the cotangent bundle of sigma 0. So let me call it T star sigma 0, which has a natural projection. So each fiber is the cotangent plane. And there is a projection to the base. And here you have an immersion. You have an immersion which, to a point of the curve, gives the point here in T star sigma. It gives the point x on y dx. So x is the point in the base, and y dx is the value in the fiber. So that's typically what a spectral curve is. And this is typically also what you find in teaching systems. So, not so much. Okay. I need to say, so on the picture to have in mind is this picture. And you see, you can have some points, some ramification points. The ramification points are, well, they can be found in two ways. One, so if A is a ramification point, it basically means that two branches of Y meet at a point. Or, in fact, there is another way to see it, is that the differential dx vanishes at these points. And let me consider only the... So I need to speak a little bit about ramification points. So, ramification points. Well, I will not enter really the details, but they are, so let's say I will stick only to simple ramification points. So that means when exactly two branches meet, and basically locally it looks like a square root. So locally, so y behaves like ya plus square root of x minus xa. Okay, and if you use, in particular, if you use the coordinate square root of x minus xa, it's a good local coordinate near the ramification point. And what I just need to say is that there is an involution that exchanges the two branches on this map. So, well, first a is a 0 of dx, of the differential dx. And just this example. So here, for my example for area, x was z squared, so dx is 2z dz. It vanishes at z equals 0. Ramification point is at z equals 0, and indeed at z equals 0, you have y equals square root of x. That's really the ramification point. And this curve is clearly the curve yx. The pure square root, and the ramification point is at z equals 0, x equals 0, which is a 0. So a is a 0 of dx, and there exists a local involution. Let me call it sigma a, which is the involution that sends square root of x minus xa to minus square root of x minus xa. So it's just the involution that locally exchanges the two branches. If your curve was of degree 2, this involution is in fact global, it's the hyperelliptical involution. But for most curves, it is not, it is defined only locally near branch points. Now let me go to, so now we have all what we need to define topological recursion. Topological recursion. So now we have our spectral curve and we want to define its omega gns. First, let me define the kernel. That's called the recursion kernel. And let me define it as an operator that goes from what I will call M1 of sigma, which is the space, which is the sheaf of, the space of meromorphic forms on sigma, tensor M1 of sigma to M1 of sigma. And it will be defined in this way. If I take two one forms, so if I take omega 1 and tensor omega 2, so two one forms, two meromorphic one forms, what should I put in the right hand side? Let me call it k of omega 1, omega 2. And so the recursion kernel will be k. And the definition is that k of omega 1, omega 2. So it will be a one form, and let me give the value at a given point, let me call it z, will be sum over a equals ramification points, residue when a variable z prime goes to a of 1/2 of integral from z second equals z sigma a of z prime to z prime, b of z prime, z second, sorry, divided by y of z minus, well, let me write it y of sigma a of z, but to be more correct, you should call it the pullback by sigma a of y, okay, dx of z, times omega 1 of z prime, sorry, so z prime, omega 2 of sigma a of z prime. Okay, it may look really strange thing. Well, first of all, one thing which is strange to lots of people that have not seen before, there is a dx at the denominator. So it's a -1 form, if you want. But remember, there is a dz prime here and a dz prime there. So in fact, you have a quadratic differential divided by differential. It's a 1 form. So locally, it's a 1 form. It's defined, so since there is sigma a, it's defined only locally in the neighborhood of a branch point, but that's fine. That's all what we need to do residues. The local definition of a branch point is far enough. The variable z appears only here. The variable z of the output is only in the B. Okay. So this looks a very strange definition, but this operator is well defined. And when you apply it to a pair of 1 forms, you get a 1 form. Okay. It looks like a strange idea to introduce this object, but this is what works. Okay. So now we have the definition of topological recursion. So definition of invariance.
How did I know which B to use?
Sorry?
How did I know which?
The B that was used to define your spectral curve, I mean the B of your spectral curve. So indeed, if the only thing I give to you is the equation, is this equation, is there a canonical B associated to this equation? Well, the answer is more or less yes. There is a canonical, there is nearly a canonical B. You have some arbitrariness, but in fact, choosing a spectral curve means also choosing the B. If you choose a basis of A and B cycles like there on the torus, you have a canonical one.
In principle, I can use the same curve with a different.
Yes, of course, yes. And in particular, you could exchange the A. So in fact, in this example, my B is the one which vanishes when you integrate it on the A cycle. But you could choose the one that vanishes when you integrate it on the B cycle. That would be another B. And you would get over another K, I mean, you would get another topological recursion, and you may wonder how are they related. And I will talk about that later. They are related. Okay, so definition. So in the definition, well, omega 01 is just y dx, our 1 form. Omega 02 is our also 1 form. So this part is easy. And then for 2g minus 2 plus n strictly positive, you define the omega gns by recursion. So let me write it this way. Omega z1 zn equals k. So let me write what it is. K omega t minus 1 n plus 1 of, let me write a dot z2 zn and evaluated in z1 plus sum g1 plus g2 equals g sum over I1 I2 equals the variable z2 zn of K of omega G1 1 plus cardinal of I1 dot I1 tensor omega G2 1 plus I2 dot I2 evaluated at Z1, and I will add something that I will ask here, no 0 in this double sum, so I should write it as a double sum. Okay. What do I mean here? You see that K needs a one form tensor one form. But this omega G minus 1 and plus 1 is a one form in each of its variables. So you just apply the K to the two first entries. You apply K to that. The other variables Z2, Zn, somehow they are spectators in the story. I just tensor. So you just get a tensor product with one form in Z2, Zn, but they are spectators. And the result is a one form in Z1. So in total, you get, when you do that, you get a one form in Z1, tensor one form in Z2, tensor one form in Zn. So indeed, it's a one form in each of these variables. Okay. And here in this sum, you again K needs to be applied to one form tensor one form. So you apply it to the first on the first there. Okay. And here you have, yes, and here again, the other variables Z2, Zn, they all appear either there or there in all possible ways. And so in the end, the result is indeed a one tensor one form n times. However, there is something a little bit strange in this way of writing. So this is the definition. So this is the definition. And you can check that indeed, if you have only omega 01 and omega 02 at the beginning, with this definition, you can compute every omega gn recursively on 2g minus 2 plus n. So in fact, you need 2g minus 2 plus n steps to get omega gn. Yes. But there is one thing which is strange in this definition. Z1 seems to play a very different role compared to all the other Zi's. So is it? But here I write it in this way, like if it were symmetric. In fact, you can prove, and you prove it by recursion, of course, you can prove by recursion that the result is always symmetric. This is not trivial. Well, it's not very difficult either, but so the result is always symmetric. So let me mention some properties. Some properties. So first, omega gn is k sigma tensor n times, and it is symmetric, and it has poles at the ramification points at any orders. So it is a one form for each copy of a curve. So in each variable, it's a one form, and it's a tensor product of these. And it can have poles only at ramification points. No one else. I mean, this is for 2g minus 2 plus n positive. Because it's not the case for omega 01 and omega 02. Omega 01 can have poles, let's say, at infinity, and omega 02 has poles on the diagonal. But all the other omega gns, for example, don't have poles on the diagonal. Okay. And they are symmetric, which is a very important property. Another property that we need, yes, in fact, there are plenty of nice properties. And for example, modular properties, which I will not talk about, but this is more or less your question. what happens if I change the B? For example, if I go from the B that was normalized on the A cycle to a B that is normalized on the B cycle. So I make a modular transformation. What happens to the omega GNs? They change in a very nice way, and this is related to a BCOV equation and things like that. I will not enter the details, but basically well, in fact, the omega GNs are quasi-modular forms. Well, another property that I will need is homogeneity. So which means that, let me define what I call rescaling. So if you take lambda belongs to C star, what I call a rescaled spectral curve, lambda, what I call lambda S, is just the same sigma, the same x, but you multiply ydx by lambda on the same B. So rescaling the spectral curve is just rescaling the ydx. In fact, if you think in terms of Higgs field, it's just rescaling the Higgs field. And the property is that omega gn of lambda s is lambda to the 2 minus 2g minus n omega gn of s. And this is almost obvious because if you remember what k was, the y dx was appearing only in the denominator to the power 1 in the denominator. So if you apply 2g minus 2 plus n times, you get this power of lambda. This is kind of obvious, but useful. And the next properties that I will really need to understand is deformations. But this is the topic of the rest of the lecture, so I will not say exactly what it is, but the nice thing is, now, when we start to have not one spectral curve, but a family of spectral curves, how do the omega GNs change? So if you have a family, let me call it ST, what happens when you do a d over dt? And in fact, all the quantization issues are strongly related to these kind of properties. So imagine you have a moduli space of spectral curves. What happens when you move into this moduli space? And this is really where you find the Hirota equations, the integrable systems, and all that. And in fact, the quantum curve is just a manifestation of the fact that there is an integrable system related to that. So, so, indeed, let's go now to deformations. Well, before we go to deformation, I wanted also to speak about I will talk about the Quantisation 2017, which is called Quantum Area Structures. Or sometimes called ABCD tensors. Okay? I will very briefly mention something. You see here that K, I define K as an operator that goes from M1 of sigma tensor M1 of sigma to M1 of sigma. This is a vector space, the same vector space on the same vector space. So if you want, you can think of K belonging to, let me define V equals M1 of sigma. You can think that K belongs to V star tensor V star tensor V. For those who know the Kontsevich-Sogelman formalism, the C tensor is also a tensor that lives in a similar space. In fact, K is the C tensor. Sogelman, there is a 1/2 of C in the equation, and here I have a K, so K is 1/2 of C. Okay, yeah, but I will come back to that later. Okay. So now we shall talk about deformations. And before giving abstract definitions, I will use mostly my examples. So,
ask a question?
or maybe it will be.
So the modular properties are already concerning the family, right? So it's
Yes,
modular.
indeed. And especially the family when you vary the B kernel.
And this already includes the. So that
Well,
will be
here I will mostly talk about deformations of a one form of ydx rather than deformation of a B. Well, in fact, deformation should concern both, but here I will focus on the deformation of a one form, which is not the modular deformations.
I was wondering, so apart from the modular properties in the family, are there also some properties if you change x and y? So if you think of it as symplectic.
This is mostly a conjecture at the moment. So in fact, in many practical examples, we see that indeed there is a nice symmetry when you exchange x and y. But in the most general case, this has not been proved.
But even under canonical transformation, so if you not exchange them, that makes some.
Yeah.
So if you think of the quantum curve as a Hamiltonian, and
so typically it would change the psi to its Fourier transform. But this is hard to prove. Really hard.
Can you think of this deformation as complex structure deformation of the underlying curve, psi zero?
I will give the examples in a minute, and I will start by example. And in fact, I will start by this example. And I will start by deforming my family here. Let me add to y this minus 1/2 of sum from k equals, let's say, 5 to d, tk, z, k minus 2. So, and then let me call it st. T is really the vector of times. So T4, T5, so T5 up to TD. In fact, only the odd times will play a role. Because you remember in the involution, you take y minus y composed by the involution. So it will kill all the even times, only the odd times will remain. So let me start from an example. Array plus deformed. In fact, I will continue after the break, but let me just give you let me not define first. Let me tell you very quickly what the omega gns are for the Airy curve. What is the value of the omega gn? So let's consider S0. And just let me mention, so omega gn of Z1, Zn, remember it has to be a symmetric, so it must be a symmetric one form, so product from I equals 1 to n of dzi, and it must have poles only at the ramification points, so it must be rational, which poles only at the meromorphic, which poles only at the ramification point, but it's poles at 0. So you have only powers of zi to the, so basically it will be a polynomial in one over zi. In fact, what I didn't say, it has also to be odd under the involution, so you can have even powers. Okay? I like to put 2 to the 2 minus 2g minus n and the minus 1 to the n. And here I like to put 2di plus 1 double factorial. Okay, in this product. And then you have to find, so then there are some coefficients, let me call them cgn of S0, d1, dn. These are the coefficients. What are the coefficients in this example? So if you take the Airy curve, so the S0, what are the coefficients? And I tell you the answer. Cgn of S0, d1, dn are the intersection numbers. Tau d1, tau dn, infinity. Or if you want, the integral of the moduli space of curves of psi 1 d1, psi m dn. For those who know what it is. So basically, this is one reason why topological recursion is interesting. So this very abstract definition with this kernel K, it produces, when you apply it to a very simple spectral curve, it produces very interesting quantities. If you had started with another curve, you could get the Mirzarani, well, the Weil-Petersson volumes. Basically, if you start from the curve, which is a mirror of a Calabi-Yau threefold, you get the Gromov-Witten invariance, and so on. So this has a lot of applications. So I will stop here. We have a break, and we'll start again after.
Thank you very much. Any questions for Bertrand?
But I'm curious, how to come up with this recursion formula?
Sorry?
How to come up with this recursion formula?
How did we come up with that recursion formula? That's a long story. It started with random matrices. It took some time before we really found the good formula. I don't know, there is a bit of trial and errors, a bit of magic. Okay, I don't know if there is really a logical path of how to say, okay, I want to compute Gromov-Witten invariance, I should write this equation. No. I can even tell you how we found the good spectral curve for the Weil-Petersson volumes with Nicolas. It was really trial and errors. So we tried to find some TKs that would produce the Weil-Petersson volumes. And the way we did with Nicolas, we made a lot of trial and errors, a lot of computer programs to compute T1, T2, T3, T4, and so on. And eventually, we realized that we were computing the expansion of a sine function. But I was not sure of that before we computed T15. And then we could prove it, but so it's mostly trial and error.
Thank you.
Other questions?
So, if I remember correctly, there exists some differential on the spectral curve, which is independent from the choice of A and B cycles. I don't remember precisely. Probably it's Bergman kernel with some logarithmic derivative of theta functions times two differentials. So, what happens if we try to substitute this kernel instead of Bergman one?
So it's the Schiffer kernel.
Probably.
In fact, there are several. There are Klein kernels, there is Schiffer kernel. In fact, there are plenty of nice kernels that you can think of, but I think that the one we're talking about is the Schiffer kernel. If you use it, that's really where you find the BCOV equations. So indeed, it leads to something. So if you use the Schiffer kernel has the property that it is not analytic in the tau variable. It contains an imaginary part of tau, but then it's independent of the choice of cycles. So it's modular invariant, but not analytic. And that's why it is related to the holomorphic anomaly equation. The anomaly is related to a holomorphic anomaly, which means that it's not analytic, but then it's modular. In fact, you cannot be at the same time analytic and modular. That's not totally true. You cannot be at the same time perturbative, analytic, and modular. You have to renounce to one of the three properties. And in fact, it's more interesting for you to renounce to perturbative. In fact, you can be modular and analytic if you renounce to perturbative.
Other questions? All right, well, thank you. So we're having a picture right now, so please follow whoever's going to be in front. During this time I just wrote, if you run the kernel K that I was writing before, so this is what you find for omega 03. This is what you find for omega 11. It's just examples, and you see we can do that. In fact, we now, well, I will For people who are interested, I will say it later, we have put online a package, a Python package, which can be used with SageMath for topological recursion. That's already available publicly. I will write the link later. But you just basically, to get these quantities, you just have to press the button. And so this is omega 03. You see, it's indeed something that is a polynomial in 1 over zi squares. And there is a coefficient minus 1/2. And if you compare to this formula, that means exactly that C03 of 0, is 1. So it's 0 to a cube, 0. This one is C11 of 1. It's 1 over 24, which is indeed the intersection number T11. If you are familiar with moduli spaces of Riemann surfaces, this is some classical things. But you can recover them through topological recursion, even if you didn't know what are psi classes in moduli spaces of curves.
Can I just, so this equality, so what's the nature of the proof? Is there some kind of conceptual understanding why there's an equality, or is it...
The equality here,
yeah.
So here this is a theorem, yeah. So you have to prove it. Okay, the way to prove it is basically to prove that both sides satisfy the same zero constraints, for example. In fact, none of these proofs is very easy. So in fact, the nature is like mirror symmetry. So the idea is that you have an enumerative geometry problem. Typically, this is an enumerative geometry problem. You want to find, and you want to ask the question, is there a spectral curve for which topological recursion will compute the same quantity? And that's why you have maybe to do trial and errors and all that. And you have to prove that indeed it gives the same quantity. Or even if you have a guess, or if you have tried on the computer and checked that all the first two ones are indeed okay. So you have to prove it, and you have to prove basically mirror symmetry. And it's never easy.
But how do you prove? What's the crux of the proof?
Prove that both sides satisfy the same equations.
So you kind of need to derive. Okay, I understand.
Yeah. Or you can, for example, use the Koncevich. You know, Koncevich wrote these quantities in terms of sum of graphs, Strebel graphs with some weights and all that. And from this, by doing recursion, removing recursively edges of these graphs, you can prove that the left-hand side satisfies topological recursion. But it's never easy.
So maybe for the intuition, you could say that the right-hand side of the topological recursion is what happens. It's contributions from the boundary of the moduli space of the left-hand side, right? So on the left-hand side you have Gn, and the two terms on the right-hand side are what happens when the genus G degenerates, or
no, it's
when
more complicated. It's not simple.
But that's more what VCOV.
Oh yes, but it's not VCOV.
Yes, I mean, because the question came up where you would come up with something like this. So it seems natural.
Well, you can prove BCOV from TR, but I don't know if you can prove TR from BCOV.
If you ask the question, if we came up with this idea by having this structure of boundary, or it's not the case.
No, yes, indeed. So in fact, it's really like in Mirzarani, it's really related to Mac-Chain identities. Okay. You have to go through something like Mac-Chain identities. There is no direct proof. It's not just cutting a perf point. It's not that. It's not degenerating the surface. It's definitely more complicated. And there is nothing. I mean, you really have to go through something like Mac-Chain. Okay. So
if you want a relation to geometry, you can Google geometric recursion.
Yeah. Yeah. So topological recursion is doing that at the level of generating functions for computing numbers, and at the level of the objects themselves, it's called the geometric recursion. And indeed, it uses Mac-Chain. Okay. So just before I go any further, so let me remember what I was saying that lob psi. Remember that lob psi was sum over g on n, h bar to the 2g minus 2 plus n, over n factorial, equals omega g n from z, infinity. And here let me take n strictly larger than 0. let me not take n equals 0 because n equals 0 just would not depend on z. It would be like a constant term. So let me write the first few terms. So you have h bar to the power minus 1 times the integral of omega 0, 1. In fact, omega 0, 1 cannot be integrated to infinity, but omega 0, 1 is y dx. It's very simple. In this example, y dx was z times 2z dz. So it's 2z squared dz. So it's the differential of 2/3 of z cubed. So when you integrate omega 0, 1, you get 2/3 of z cubed. Plus, now you would have integral of, so the order h bar to the power 0, the only term here is omega 0, 2. So you have to take a double integral of b. It has to be regularized a little bit, so let me tell you what the answer is. So h bar to the 0 on 1/2 of log of 2z. That's what you get when you do the integral of omega 0, 2. Plus h bar, and here at order 1, what you would get would be the integral from infinity to z of omega 1, 1 plus 1/6 integral of omega 0, 3 with the infinity. That's the only terms that contribute to order h bar. And I've written them here. So this is omega 1, 1. Integrate with respect to z one time. You get 1/48. Yes. So you get 1/48 z cubed plus 1/6 times. So you integrate each variable from infinity to z1. So the integral of dz1 over z1 squared gives minus 1 over z1 times minus 1 over z2 times minus 1 over z3. But you take the three z's to be equal, so it's minus 1 over z to the cube times minus 1/2. So basically we get 1/2, 1/2, 1 over z cube. Okay? If you add that 1/48 plus 1/12, that makes 5/48. And which is indeed the coefficient of the expansion of the every function, 5/48. The first term. So it's 5/48. So 1 over z cubed is like 1 over x to the 3/2. And so indeed this is the correct coefficient that you would get in the every function. It was just to illustrate. And this is exactly what you need to make sure that h bar square d psi over dx square minus psi. So if you use this, if you just use this expansion toward h bar as I wrote it, you will see that you get an O of h cube or something like that. But in fact, you can go as far as you want, you will always get 0. So indeed, which means that indeed this psi is doing the quantization of the curve y squared minus x equals 0. Again, this is too low. So now let me go to deformations, really. So, when we do deformations, so I consider a family, and I wrote what my family is. Okay, my family is there. So let me write y dx now, and remember that dx is 2z dz. Y dx is 2z squared minus sum over k tk z to the k minus 1 dz. Just let me make a small comment. If you want to extract the coefficient tk, what you can do is take the residue at infinity of y dx times z to the minus k. Remember that the residue at infinity is minus the coefficient of 1 over z. Plus, so that's why indeed we get tk. Okay, so let me put this as a side remark. And let me call it T infinity k, well, which I call Tk. So it's the residue at infinity. And let me replace z by square root of x, which you can always do. So let me write x to minus k over 2 y dx. Now let's see what happens when I take a d over dk of y. D over dtk of y, well, it's minus 1/2 z to the k minus 2. But let me multiply it by dx. So I multiply by 2z dz, so it will be, well, in fact, it's really here, minus zk minus 1 dz, which is a meromorphic form. So it's a meromorphic form. But now let's try to write it in a way that we but will be useful. Well, let me write it as minus 1 over k dz times d over dz of z to the k. Why not? Okay. But observe the nice thing that minus 1 over k dz, and a derivative can be obtained by taking a residue with a double pole. So let me write it as residue when z prime goes to z of 1 over z prime minus z to the square z prime k dz prime. This residue will peak, so since I have a z prime minus z to the square, it will not, it will pick the derivative of z prime k at z. Just a strange way to write it. But let me observe that if I have dz prime over z prime minus z to the square, it's exactly the b. So let me write it in this way. Minus 1 over k, residue when z prime goes to z of z prime k dz z prime. And let me observe one more thing. B has a pole at z equals z prime. But this quantity has a pole at z prime equals infinity. And these are the only poles. There is no other poles. And the sum of all residues has to be 0. So let me write it now as in this way. So it's plus 1 over k. Residue at z prime goes to infinity of z prime to the k, b of z prime. And again, let me replace that by 1 over k, residue at infinity of x to the k over 2 times b. Okay, I'm quick, but x of z prime, b of z prime. So let me put it here, this relationship. D over dtk of y dx is 1 over k residue at infinity of x to the k over 2 times b. So it may look a strange idea to write things in this way. I should have kept that here. This one equals residue infinity x to the k over 2 y dx and d y dx over dtk equals residue 1 over k x to the k over 2 times b. Okay. You could play the same game with torus. which is on the other side, and try to compute. So let me show you a little bit what you would get with a torus. With a torus, you could so with a torus, my curve is y squared equals x cubed minus tx minus v. Okay? And let me introduce a little bit like here I was introducing a rational parameterization. On the torus, you cannot use a rational parameterization, you need elliptic functions. And let me use the Weierstrass function p of z tau. So you see that here there is a puncture at infinity where y behaves like x to the 3/2, which means that x has a double pole and y has a triple pole. The Weierstrass function has a double pole and its derivative p prime has a triple pole. And in fact, it is well known that p and p prime, the Weierstrass function satisfies differential equation, provided that, so you see here the curve is parameterized by two parameters, t and v. Whereas this parameterization here, I use two parameters, tau, the modulus of the torus, and a number which I call nu. And if you see, if I change nu, it will not change the fact that y is like x to the 3/2 at infinity. But so tau and nu are just another way of parameterizing, and so it means there is a relationship between TV and tau nu. This relationship is written here. G4 is the fourth Eisenstein series, and G6 is the sixth Eisenstein series. If you know elliptic functions, this is quite obvious. But so basically, you make the change variable from TV to nu or tau. But in fact, it's much more interesting to introduce another quantity, which is the period integral epsilon. So let me introduce the period integral. I didn't write it, but epsilon here. Epsilon is 1/2 pi I integral over the A cycle of y dx. So if I introduce this period, in fact, I prefer to parameterize my curve. So it needs two parameters, either TV or nu tau, but I prefer to use t and epsilon. So let me parameterize it with t and epsilon. And you can invert these relations and find epsilon as a function of tau, nu, or whatever. Okay, you can invert it, it's very easy. And now let's call it the spectral curve of t epsilon. And, well, so first remark is that t, you can check, I let you compute, it is the residue at infinity of x to the minus 1/2 of y dx. Well, it's a little bit similar to what we obtained there, you see. It's not totally accidental. On the epsilon, I will call it 1/2 pi I, integral over the A cycle of y dx. Well, now I let you do it as an exercise. You can compute d over dt of y dx. Be careful, this is a d over dt at constant epsilon and at constant x. So since x itself is written as a function of nu tau z, you should think that z should be seen as a function of x, but which depends on nu and tau, so it depends on t and epsilon. So you have to be careful when you take derivatives, work at x constant. When you do that, you can write the result as a little bit like here, residue at infinity of x to the power plus 1/2 of b. Well, more or less the same formula we had for Larry. And you can now do the d over d epsilon of y dx. Now at t and x, it's the b cycle integral of b. So, I mean, so this is a function of a variable z. So here you have two variables. One is the one that you integrate there, and one is the one that was the variable here. So you integrate the first projection, and what you get is the one form in the second projection. But so you see that each time you write the derivative of y dx with respect to any of these parameters in the family as an integral that contains the b. Let me give you a hint of what we are going to see later. Let me write this theorem. I really need to introduce a little bit more formalism. The operation of taking one form, multiplying by x to the 1 of and taking the residue, is a linear operation that acts on one form. So it belongs to the dual of a space, to the dual space of one form. It's a linear form with a space of forms. Okay. So let me introduce. So let me define this operation. Let me define the operation that I will call B infinity k. It goes from the space of one form to the space to C. So basically, which means, in other words, that B infinity k belongs to M sigma dual. The operation is that whenever you have a one form, let's call it omega, associate to it 1 over k residue at infinity of x to the k over 2 omega. So it's just a linear map acting on the space of one form. Or since it belongs to a dual, very often I prefer to write that as a pairing. B infinity k omega. So, I mean, this is, sorry, I'm going to write it as a pairing. B infinity k omega. So I use the pairing notation. In fact, the pairing between, so the dual of a space of forms, very often, an easy way to get something dual to forms is to use cycles. Usually, when you have holomorphic forms, it is dual to cycles. Here we have meromorphic forms, not holomorphic, so it's a little bit subtle. So that's why I will call the dual to be, I will call them generalized cycles. But the important thing is that it's element of a dual. And to mimic the Poincaré duality with cycles, let me, but this is just a notation. But it's very convenient to use. Let me write it as an integral. It is merely a notation. But it's reminiscent of the form-cycle duality of the Poincaré pairing between forms and cycles. It's very convenient to write things in this way, but you have to keep in mind that this really means take omega multiplied by x to the k over 2 divided by k and take the residue at infinity. Okay. I will also introduce A infinity k will be, so whose pairing with a one form will be basically the residue at infinity, x to the power minus k over 2 omega. And I do not divide by k, but instead I multiply by 2 pi. Why not? So it's another example of this. So A infinity k also belongs to the to M1 of sigma star. Well, you could think I could do the same kind of things for every element of a dual. But let me tell you, the dual of, well, the space of one form, M1 of sigma, one form, is of infinite dimension. It's not quantably generated, because you can have poles at every point of the surface of any degree. It's not quantably generated. And the dual is something very nasty. The dual of that space is extremely nasty. Typically, in the dual, you could take things like integral of omega on any domain D times a measure on that domain, so mu. So take any domain, any measure mu, and compute this quantity. It will be a one form. It's a linear form. But the result, you can even take a fractal domain with a fractal measure. It's very, very nasty. You don't want to do that. So let me make a definition. Let me make a definition. And let me call that general cycles. So this is the space. So let me call it M1 of S. It depends on my full spectral curve. So it's the space of all, let me call them gamma belongs to M1 of sigma dual, such that when you integrate, so let's say when you take, such that gamma B in the first projection belongs to M1 of sigma in the second projection. Here. So B has two variables. We integrate the first one with gamma, we pair the first one with gamma. The result is a one form in the second variable, and you want this one form to be meromorphic. In fact, if you take this nasty thing I was saying before, integral of a fractal domain and all that, the result will be one form which is nowhere analytic. You can get one forms that are even nowhere continuous. So the dual, if you take the full dual, this quantity is a very nasty one form. You want to keep only those that lead to something meromorphic, and that's what you call generalized cycles.
So just for notation, S on the left side, it's because on the right side it depends on
sigma
and
exactly.
B?
Yes, exactly. Because to define this space, you need not only sigma, you also need B.
So you just actually need part of the data, only sigma.
But now this space is nice. This space is much nicer. Its dimension is almost, well, naively I would say twice the dimension of the space of meromorphic forms. So it's usual. The dimension of cycles is twice the dimension of forms. And in fact, it's a symplectic space. And so in fact, let me add a few more definitions to that space. So let's define the map B hat to be the map that goes from cycles to forms, that we cycle gamma associate gamma B, which I will also write gamma B, okay, which also very often I will write omega gamma.
Ask a question? So for the d by dt and d by d epsilon of y dx, you probably need to use some connection. You're using a Gauss-Malin connection on the space of forms, or?
Yes, in principle, but here we have very explicit examples, so I mean it's kind of obvious.
No, I was wondering whether instead of having this pair, so if you take d by d capital V of y dx, then you just get a geometric form.
Sorry.
So you have the Gauss-Malin connection there, so you can say what the outcome of acting with these vector fields composed with the Gauss-Malin connection is on the forms. So.
Well, yes, but here you have a very explicit family, so you can just compute the derivative. I'm not sure I understand your question, but I mean here it's very trivial. What I want to mention is that each time that you compute a d over dt of this one form y dx, what you will find is always a pairing between a generalized cycle and B. So it's always of that type. Okay. Well, so again in the definition, let me define an intersection gamma 1 intersection with gamma 2. By definition, it's 1 over 2 pi I integral over gamma 1 of this integral over gamma 2 of B minus integral over gamma 2 of integral over gamma 1 of B. So you see, by definition, this quantity is a meromorphic one form. You can integrate it, you can pair it with gamma 1. And that gives a number. And then you do the things in the opposite order. Since B has a double pole on the diagonal, if the two cycles intersect somehow, this does not commute. So in fact, you can take that as the definition of intersection. In fact, well, I should have said that if you take standard Jordan arcs or Jordan loops, they belong to that space and they give the usual cycles, and this gives the usual intersection.
Is that the pairing of B, or?
Sorry?
Is that the pairing of?
Yes, this is the pairing. So this integral of gamma of B means exactly, so this was the notation for this pairing. Okay. And some theorem. So theorem. Let me just mention a few theorems. So first, that the map B hat from M1 to M1 is surjective. It's not injective. And in fact, curl B hat is a Lagrangian. And the intersection is non-degenerate. The fact is Lagrangian means, well, the fact that the intersection vanishes on curl B hat is quite obvious, because indeed you take the pairing with B, so if gamma 2 paired with B vanishes and gamma 1 paired with B vanishes, of course the intersection vanishes. So the fact that the intersection vanishes in curl B hat is obvious, but is it enough to make it the definition of a Lagrangian? No, in fact, what you want is that the full space M1 is curl B hat plus L, where L is also a Lagrangian where intersection vanishes. So it's really what you need to have Lagrangian. So that's also a complement which is Lagrangian. And the choice of L is not unique. So now we go to well. So now if you take my cycles here, let me tell you that A infinity K intersection with B infinity J is delta Kj. That's why I put this 1 over K on this 2 pi I here. I wanted to get this. If I didn't put the 1 over K or the 2 pi I would not get that. And also I wanted, so the 2 pi I is because when K equals 0, I really wanted it to be the contour integral. Without the 2 pi I. I mean, residue is with 1 over 2 pi I, but I really wanted the contour integral, so that's why I really need this 2 pi I here on this 1 over K. Otherwise, it will not be a symplectic basis. Okay. So, this is my definition of generalized cycle. So, now what have we obtained? Well, first of all, you can do it as an exercise, verify that this B infinity K and A infinity K are indeed generalized cycles, so which means that their pairing with B is indeed normal. So you have to check that, which is not, I mean, you should always check that, because there exist elements of the duals for which it will not be. Okay. So now the theorem that we have in TR, which is important, is how do we form then the omega GN. So this is one of the most important theorems in TR, is that if you have a family, ST, and imagine that, assume there exists gamma T belongs to M1 of ST, such that d over dt of omega 01, so y dx, is the integral of omega 02, so that is b. So it's exactly what we had before. So this is exactly what we found for the example of the Airy curve and for the example of the Panové one. Okay, and d over dt of omega 02 is integral of gamma t of omega 03. What do I mean by that? Here we have a 1 tensor 1 form. Here we have a 1 tensor 1 tensor 1. You contract 1 with the gamma t, and the result is a 1 tensor 1, like the left hand side. Okay? So if both are true, then for every g on n, d over dt of omega gn is integral over gamma t of omega gn plus 1. So basically, if it's true for 01 and 02, it's true for all gn. Well, this is a very powerful theorem. It's very closely linked to what's called spatial geometry, or also Cyber-Witten. Okay. Yeah, so this is one of the most important theorems. Another one is like, in fact, whatever the deformation, you will always be able to find the gamma t. But I will formulate it slightly differently.
When you write the third equation over there, do you mean that omega 02 may not be B?
Sorry?
So I thought the
If
theorem...
you don't normalize, so this is, for example, related to...
Yeah, so that was the question.
If you don't take the Bergman kernel, which is normalized on A cycles, it might not be obvious. You have to check that.
Yeah, thanks.
So if you take, for example, the Schiffer kernel, you have to check. You could choose, so basically, you may choose a B that would possibly not satisfy that. In fact, there is a way, to complete these equations by also deformation of B, but I don't want to. Okay. It's done in one of my papers.
Just a naive question. So in the case of the area deformation, so B does not depend on the TK, right?
Indeed.
So what?
But you can check that this integral is 0. So this is satisfied. So indeed, well, one theorem is that, well, basically for the Bergman kernel, this equality is the Rausch variational formula. So whenever you have a Bergman kernel, Rausch formula tells you that this is always satisfied. But let me not enter the details.
But you've got to be careful because you've got to work with x fixed when you compute the derivative.
Yes.
So Z you could...
Yeah, but here x fixed and z fixed is the same because I didn't put T1.
Yeah.
Okay. If I put T1, things would be slightly... Okay. In Paleve, for example, you have to be careful about that. Okay. Okay. So this means that for every Gn, T over d omega Gn over dtk equals 1 over k residue at infinity of x to the k over 2 omega Gn plus 1. So here I mean that you contract one of the variable with this one, and the other variables are the ones that you had in the left-hand side. If you apply this, so just as an application of this formula, just an application of, to show you that how powerful this is, just remember that if you started with, I told you that in this example, since the only branch point is at z equals 0, omega Gn could always be written as of z1, zn, and always be written as minus 1 to the n to the minus g minus n, sum over g1, dn, cgn of your spectral curve st, d1, dn, so some questions, product over I plus 1 to n of 2di plus 1 double factorial, dzi over zi to the 2di plus 2. So it's hard to read, but it's the same formula as before, except that now the coefficients Cgn, they do depend on the times. Okay. Well, here I've just written that omega Gn is the most general possible rational fraction, polynomial in 1 over zi squared. And symmetric, okay. Now, I can use this property here to compute the Cgns, or to show that the Cgns satisfy the differential equation with respect to the times. And so you see, it will relate the Cgns, the derivative of the Cgns, it will relate them to the Cg of n plus 1. In fact, it's a first order linear equation which you can solve. It's very easy to solve. And the answer is very simple. Cgn of the t's of st, d1, dn. It would be, and remember before it was tau d1, tau dn. Let me make more space. G. It was that, but now the only difference is that we have an exponential sum. So I think it's 1/2 sum over k, 2k plus 1 double factorial, t 2k plus 1. Okay. Okay, I'm not right. I think it's 2K minus 5. Okay. I'm not 100% sure. T5 is associated to tau 2. So this formula is a direct consequence of this deformation property. If you take all the tk's to be the coefficient of a sine function, you may recognize that this exponential of tau classes is a Weil-Petersen class. And so if you started with z, all the tk's to be the series of a sine function, you would get the Weil-Petersen class. So you would get that the TR gives you, the omega GNs of TR give you the Weil-Petersen volumes. And this is a direct consequence of just this property. So this is one way to prove Mirza's relations.
Can I ask another? So in your theorem, the t is a distinguished coordinate, right?
Sorry?
The d by dt, that's a distinguished vector field.
Yes.
So in your Panevet example, you have t, v, tau, nu, and epsilon.
Yeah.
Which one of them is the one satisfying?
Okay. So I'm going to talk indeed about the Panevet one. So for the Panevet one example, so let me tell you what happens in the Panevet one example. So here you have only two vector fields that are d over dt and d over d epsilon. Okay, and basically the same will occur. So I told you that the d over dt is this b infinity 1 cycle integral, and the d over d epsilon is just the usual b-cycle integral. And in fact, so that means that for that case, for every gn, d over d epsilon of omega gn is the integral over the b-cycle of omega gn plus 1. That's in fact somehow Seiberg-Witten. And d over dt of omega gn is residue at infinity of x to the k over 2 omega gn plus 1. So it's immediate. So basically, once you have computed d over dt of y dx and d over d epsilon of y dx and written them as integrals of b, then the rest is immediate.
Yeah. In the second equation, it's k equals 1, right? X to the power 1 half.
Because t is t1. So this is just some example of applications of this. Now, indeed, your question was regarding vector fields. So in fact, so now I want to make the link between general cycles, Vs, tangent, vectors. Okay. So basically, how to associate the gamma from the d over dt. So in fact, what I've shown you so far is that whenever I have a vector field like d over dt, d over d epsilon, so that's the tangent vector, you can associate to it a generalized cycle. In fact, this association is not unique. If I give you a d over dt, there are many generalized cycles which you can associate to it, just for a simple reason. There exist some cycles. So for example, you can add to gamma any cycle on which the integrals of the omega GNs are vanishing. And this is related to the fact that this map B hat has a kernel. So there is a kernel. So the map that gives from so the map that goes this way has a kernel. No, sorry. No, sorry. The map that goes this way is ill-defined because you don't have a unique gamma that you can associate to a vector field. You have many. It's because, in fact, we should regard the mapping on the other side. On the map on the other side, has a kernel. And the kernel is really big. Let me now define the mapping this way. So, we can look from a map that goes from general cycles to, let me call that the tangent space at my spectral curve of the moduli space. So let me call that SP curves. So in fact, all this has to be defined in the world of categories. So SP curve is a category of spectral curves, and the tangent space is in fact a stack or sieve. Okay. I'm finishing to write the paper on that, but in fact, you have a category here on which you have Grothendieck topology and things like that for people who know what I'm talking about, but for the moment, let me be quite informal. And the idea is that to a cycle gamma, let me associate a vector field that I will call d gamma. And the only thing we shall need in this talk, well, okay, this can really be defined in this category, but I don't want to say that at the moment. So what it means is that to a gamma, you can associate a family. There exists a family, a one-parameter family. But what I really want to use now is that, by definition, the d gamma is such that d gamma of omega 01 by definition is integral of gamma of omega 02, and d gamma of omega 02 by definition is integral of gamma of omega 03. That's the definition of d gamma. So basically it tells you how it deforms the spectral curve. So how it deforms omega 01 and how it deforms omega 02. So if you want how it deforms y dx is integral of gamma of b, and d gamma of b is integral of gamma of omega 03. This is the same thing. And the theorem is that for every gn, d gamma of omega gn is integral of gamma of omega gn plus 1. So in other words, to every vector field, to every cycle, you can associate a vector field. The inverse map is not well defined because this map has a kernel. It's not injective. This map is not injective, but what can be proved is that it is surjective. The proof is not straightforward. I'm finishing to write the paper, but okay, the proof is not. Okay. So, okay, so where am I now? I think I'm a bit late on my schedule. So,
can I ask another question? So earlier you told us that this omega gn, how it behaves under rescaling.
Yeah.
So I think technically you could also write down a third vector field acting on omega gn that has.
In fact, rescaling the spectral curve is equivalent to rescaling both t and epsilon. So in fact,
yes, so I'm just saying, so in this case for the cubic curve, there is a triple of vector fields, so two of them are the ones you have.
In fact, you can even do more than a triple. You can even deform it in different directions.
Yeah, so I'm saying there is a triple, and the third one would give you this rescaling weight, and then they form an SL2C.
It's slightly more subtle because the rescaling is not independent of this. It's not an independent direction.
Yes, but so are not epsilon and t, but you're treating them as independent. So the moduli space is just complex one-dimensional.
Well,
I'm saying you can enlarge.
In this map, now I'm associated to a cycle tangent vector, and I don't require my tangent vectors to form a basis or to be independent. I mean, you can have two different gammas that give maybe two gammas that would be proportional. It doesn't matter.
I'm just remarking that you could even enlarge this more and include the rescaling of the form. And then,
of course, you could. You can take any deformation, any one parameter family you like. So in particular, just the rescaling family is just one particular one.
If you take tau here, the cycle, so if you take derivative with respect to tau for the Weierstrass curve, what would be the generalized cycle?
Exercise. Well, I must say now, okay, now I have to introduce two more notions. So one notion which is particularly important is the insertion operator. So definition, insertion operator. Well, okay, sorry, before that, I need to introduce a family. So, let me define. So definition. So for every, let's say P is a generic point on sigma. And let me introduce this B, pk, a general cycle. So let me define it in this way. Bpk by its pairing, bpk paired with a one form omega is residue. So, and that will be a k positive to z plus 1z positive. 1 over, so residue when z goes to p, let me call it z prime, x of z prime minus x of p to the power minus k times omega of z prime. If p was a ramified point, was a point at which x is ramified, let me divide by order at p of x. So this is why when we had infinity, which is not a generic point, at infinity that's what, which was ramified of order 2, that's why we divided by 2. So that's the definition of visibility. And you can check that it is a general cycle. So if you contract it with the omega 02, it gives a meromorphic one form. So then the definition of insertion operator. Let me call it delta P. Delta P is by definition is the P1. And let's multiply it by dx of P. So delta belongs to H0 of sigma and K sigma tensor CS of SP curves. So if you want, delta is a vector field, so it's a derivative. It's like a d over dt multiplied by a dx. It's a one-form valued tangent vector. Tangent field. Well, let's compute what it does when it acts on omega gn. And you will see where the name comes from. If you act with delta p on omega gn of z1 zn, by definition, this is dx of p times residue when z prime goes to p of 1 over x of z prime minus x of p. Let me take a generic p, okay, which is not ramified. Let me take a generic p times omega gn plus 1 of z1, zn, and p on z prime. Since we are taking the residue of a simple pole at z prime equals p, it just evaluates, and the result is just omega gn plus 1 of z1, zn, and p. So the only effect of delta p is to have added the variable p. It has inserted p, and that's why it's called the insertion operator. Okay. Now, okay. So this operator is very useful, and in fact it's the right way to write the Eynard constraint is to use this operator. And also, let me very quickly write what are the so ABCD, and I think it was part 4 in my talk. No, 3 or 3. The ABCD, so the Kontsevich-Steubelman 2017 formalism. And what Kontsevich-Steubelman wrote is that well, they try to reformulate topological recursion as writing that the deformation of the partition function can be written as a sum with tensors acting on some vector fields. Let me write the formula. So let me define Z of my spectral curve, H bar on S. Let me write it as exponential sum over G of H bar to the 2G minus 2 omega G0 Omega G0, very often people call it FG in the literature. Ricardo was doing this presentation. And how does, then topological recursion is completely equivalent, so let me write it as a theorem. So if you act with delta, so H bar delta Z of this Z, H bar S, is equal to, and here, I will use this term K. Well, okay, let me not put the Z here. K, okay, K needs to act on, okay, let me write the formula. Let me write the formula, let me explain. Remember, the kernel K needs to act on a pair of one forms. So the delta acting on Z, by definition, delta, as I said, when it acts on Z, so it takes a kind of derivative of Z and produces a one form. You take a second delta, so we have a delta tensor delta that will produce a one tensor one form. So delta tensor delta acting on Z produces a one tensor one form, which you can put at the entry of K. And the result is a one form, which is a delta acting on Z. In fact, this equation is nothing, on omega 1 is a one form, multiplied by Z, which is a, Z is a scalar, Z is a function, Z is not a one form, it's a zero form, it's a scalar. So omega 1 is a one form times a scalar, so this is a one form. On the left hand side is a one form. And this equation is exactly the Kontsevich-Sobelman equation, but it's also just a mere rewriting of topological recursion. So if you expand into powers of H bar, you will write that this is the, so let's say the coefficient of H bar to the 2t minus 2 plus n on each side. Here we will get that this is the left-hand side of the topological recursion, and here this K is exactly the right-hand side of topological recursion. In fact, this is a mere rewriting of topological recursion, but it is also the equation of Kontsevich-Sobelman. And so, the only thing that regarding Kontsevich-Sobelman is that here we have a concrete choice of what is the vector space. The vector space is the space of meromorphic manifolds. Basically, this is the C tensor, and K is in fact at the same time the C, the B, and the A tensor. And this one is the D tensor in Kontsevich-Sobelman. The reason why it's at the same time the A, the B, and the C is that sometimes, so basically each time delta produces omega 0, 2, you cannot call it the C, I mean, you call it the C tensor only if it's not omega 0, 2, otherwise if there is one omega 0, 2, you call it B, and if there is two omega 0, 2, you call it well, it's time. Maybe in a couple of minutes I can write the loop equations. I will certainly not have time to explain how to derive quantum curve equations. I just introduced the formalism. But in fact, this is the good formalism to write quantum curve equations. Maybe in a couple of minutes I can write the loop equations or the Virasoro or double algebras as you like to put them, if you want. Okay.
Oh, sorry, before you raise a small question, this insertion operations looks very like this coproduct, whether this is some coproduct interpretations?
Yes, yes, it has an interpretation.
But which algebra is?
Which?
This is the co-product of which algebra?
Okay, maybe let's discuss that later.
Can I also ask about this sensation? To me, it kind of looks almost like a Gauss, like a very trivial Gauss-Manin connection on the space of spectral curves.
Yeah.
And so then, can I kind of interpret that theorem to say that topological recursion is some kind of Gauss-Manin equation? Oh, I see.
There is a Frobenius manifold structure on the space of orbit curves, and which we can identify as the space of spectral curves. So you think of your spectral curve as a point in the orbit space, actually a cover of the orbit space. And there is a Frobenius manifold structure there, and these formula are basically what you do.
Okay, so let me come back to this picture where for a given x, you have zi of x, preimages. I equals 1, 2, 3, 1, 2, 3, and so on. Let me define the following operator. Let me call it wk of x. Let me call that wk of x, so it depends on the point on the base. It is, by definition, it is sum from I1 ik, which is related to the degree of the curve. So the highest term is d, okay, of delta z1 of x, tensor delta I1 ik of x, and you project that to the base. Okay. So written in terms of base. So what is this operator? This operator is a tensor product of k one form, so it's a kth order form. It's a kth order form on the base, and it's a tensor product of derivative k times. So it's a kth order differential operator in the moduli space. So let me this one belongs to H0 of sigma 0, so the base. K sigma 0, to the power k, tensor Ts, the module, the tangent space, to the power k. So it's a kth order differential operator valued in kth order forms. That's very close to this notion. Okay. In fact, it's related to the W algebra. They satisfy W algebra. And in fact, W2 is the Virasoro operator. W2 is Virasoro. W2 is called the stress energy tensor. So in both examples that I wrote, we had only a two-sheeted curve, okay? And in both examples, we had a two-sheeted curve, and the evolution was just z of x and minus z of x. So in my example, in our example, in our degree 2 example, we have that W2 was delta z of x, tensor delta minus z of x. So basically, when you act with W2 on some omega gn, it will insert two new points that will be z and minus z. If you remember, this is exactly what we had in the right-hand side of the topological recursion. We had some omega g minus 1 and plus 1 with z and minus z. So in fact, the W2 is exactly what produces the right-hand side of topological recursion. On the theorem, the theorem, which I call loop equations. There are several versions. Theorem, which can be called loop equations because it was called so in the context of matrix models, which you can also call W algebra or Vira-Zoro. So Vira-Zoro is really when you have two sheets. W algebra is when you have more than two sheets. Is that so for every k, wk of x applied to z, so it will produce it will produce a kth order form. So the result is a kth order form, and remember that. So let me be more explicit about what it means. Z equals exponential sum over g h bar to the 2g minus 2 fg. So when you first apply delta z to z, you will get sum over g h bar to the 2g minus 2. Fg was omega to 0, so we get an omega g right to z times z. When you apply a second time delta minus z, delta z to z, you will have the delta minus z, sometimes you will insert here or you will insert there. So you will have a sum over g h bar to the 2g minus 2 omega g1 of z times sum over g h bar to the 2g minus 2 omega g1 of minus z plus sum over g h bar to the 2g minus 2 omega g2 of z on minus z. Everything multiplied by z. So it's a formal series basically it's a formal series in H bar, and the coefficients are combinations of some WGNs. And the WGNs have poles at the ramification points to an order which goes with the G. Okay? So, which means that the right-hand side is a combination of many things that have poles at ramification points. And the theorem, which I was mentioning, the theorem is that this quantity has no pole at ramification points. So order by order in H bar, all the poles should cancel. And in fact, this fact is totally equivalent to the topological recursion. So the fact that they cancel is precisely on vice versa. If you say that the right-hand side has no pole at ramification points, you can try to isolate in this product the terms where you have omega gn times omega 01, put it in the left-hand side, multiply by k, compute a residue, and because k has a simple pole at coinciding points, it will just produce your omega gn. But because it has no pole, because the total sum has no pole at ramification points, it means that this residue is minus the residue of the rest, which is the right-hand side of the topological recursion. So I mean, it's very sketchy, but the fact that it has no pole implies topological recursion, and topological recursion implies it has no pole. This is more or less equivalent. Now you can do even better, and I will finish. Not only it has no pole, but you can even say what it is exactly. You can even say what it is exactly, and this is the way to prove quantum curves, so that's why. Okay, it has no pole at ramification points. It's a kth order form, it has no pole at ramification points, but of course it must have poles somewhere. So where could it have poles? In this big product here, somewhere there is some omega 01 and omega 02. All the stable omega gn, so with 2g minus 2 plus n, have poles only at ramification points. But omega 01 has poles at infinity. And omega 02 has poles on the diagonal. So in fact, this quantity can have poles on the diagonal and at infinity. And, I did not introduce any Z1, Z12 zone, so there is no diagonal. So there is no other points at which. So the only poles can be at infinity. So the right-hand side is something that has poles only at infinity. Let me So you, but okay, here I'm afraid it will be slightly more technical, so, but omega. Let me also define this operator. Equals sum over k equals 0 to d of minus 1 to a k, y to a d minus k, omega k of x. So it's just a way to collect all the omega k's together. Okay. So the same statement say that omega of xy applies to z. And let me divide by z. So it is something that has poles only at infinity, or nowhere else. It's a function, so it's clearly a polynomial of y. It's clearly a polynomial of y. It has poles only at infinity, which is it's also a polynomial of x in my examples. So let me call this one p tilde of x and y. It's very similar to a p of xy we started with. And in fact, it can be proved that it is very similar to a p of xy plus a series in h bar. So plus a formal series in h bar. And the formal series will affect only the terms that are at the interior of a Newton's polygon. Okay. So basically, p tilde is nearly the same as the p we started with. In fact, p tilde can be written as a differential operator. Okay. I think I should better stop there. It will be really for people. I mean, I can write a formula, but it's really for people who are really used to this topological recursion. I think I will totally lose the others if I do that. But well, the important thing is that p and p tilde, they differ. So in the case of V1, for example, they differ only by the value of epsilon, not by the value of t. So in example in V1, p, remember p of xy was y squared minus x cubed plus tx plus v. Okay, on p tilde of xy will be y squared minus x cubed plus tx plus, well, and let's write that this v was a function of t and epsilon. V on the same t on another epsilon. So the only thing you have changed is epsilon. And in fact, you can even say more explicitly in the case of V1, this is y squared minus x cubed plus tx plus d over dt of log z. So it's even more explicit.
So epsilon tilde is a whole series and it works?
Yes. Epsilon tilde is a whole series of functions. Well, so now this, arriving to this equation is in fact sufficient to derive a problem. And to derive, in fact, that this whole series, this z, in fact, it's also sufficient to write that this z will satisfy errata equations, and this z, so the second derivative of log z with respect to t will satisfy the V1 equation. In fact, all this will imply that d2 over dt squared of log z, if you write it as u of t, it satisfies the V1. I don't know if that.
Maybe just another question. So do you know if exponential of epsilon tilde, will it also be a solution of the quantum curve?
Sorry?
Will exponential of epsilon tilde, is it also a solution of the quantum curve?
In fact, in fact, let me write. Okay, this is something I wanted to not have time to do, but let me write the loop equation this way for the V1 case. So for the V1 case, let me write the equation in this way: W of xy z equals y squared minus x cubed plus dx plus d over dt Z. Okay? If you write the loop equation this way, you see that nothing in the right-hand side depends on epsilon. You don't have d over d epsilon does not appear, and epsilon does not appear as the coefficient. So which means that, so remember this was z of s of t epsilon. So let me write it this way. Which means that this, so it was 0, this equation is satisfied by every spectral curve in this family. I mean, for every epsilon, it's satisfied. So it's a linear equation acting on Z. So which means that any linear combination could be solution. And I think this is what you have in mind. So let's take sum over epsilon belonging to some ensemble of let's call the coefficient C epsilon Z of S of T epsilon is also a solution of that equation. So you can take linear combinations. When you do that, the exponential term of 1 over h bar will be different for all these terms. So you can think of all these terms to be instantaneous. With respect to the term of stroke, these are SZT instantaneous. So all these terms are solutions to that. But you have to choose what coefficients of epsilon you can put. So what I'm just saying is that loop equations are linear equations, or Virasoro constraints are linear equations. Any linear combination of solutions is solution. But only certain linear combinations will satisfy Hirota, because Hirota is a non-linear equation. So to satisfy Hirota, you have to make a very precise choice of C epsilon. And in fact, the good choice is to take epsilon integers and C epsilon and exponential with some epsilon, and I think this is what you had in mind.
Yeah, so what I had in mind is the analogy with Darboux coordinates. So then you would say, okay, the Z is somehow the magnetic Darboux coordinates, and it's a solution of the quantum curve.
Yeah.
And then, but you also have the electric one, and that's the leading order exponential of the flat coordinate, or exponential of epsilon, but then it also has h-bar corrections.
Okay, I think this is what we okay. I just think we should postpone this.
Okay.
But yes, the answer is more or less yes to what you said.
Okay, well, let's thank Bertrand for going.